Okay, so we can start, I think.
Yeah, sure.
Welcome everyone. Today's speaker is Anurag Singh. He'll speak about graph complexes at the intersection of algebra, topology, and combinatorics. Go ahead, please.
Okay. Thank you, Professor Krishna, for the introduction and yeah, for organizing this series of talks. So, I'll talk about the graph complexes, which are sort of simplest complexes associated with graphs, and give you a bit of motivation of their study by people who study these complexes. So, I have sort of made this talk in two halves. The first half will be a brief introduction or brief sort of brief what people do in topological combinatorics, and the other half I'll talk about the recent work that I have done with Priya Deshpande and Sanjay Shukla. So let me start with basic definition in this area, that is a simplicial complex. A simplicial complex is a collection of sets with the property that excuse me, yeah, with the property that if you have a set in the collection, then all the subsets of the set are in the collection. So this property of having all the collection of a set in a collect all the subsets of a set in a collection is called the hereditary property. So a simplicial complex is a collection of sets with hereditary property. For example, you take K1 where you take 1 to 3, all subsets of 1 to 3 are there. So this is a simplicial complex. On the other hand, K2 is not a simplicial complex because it misses 2 and 3, 2, 3 subsets. So these are the terminologies that people use in simplicial complexes. The first one is any element of a simplicial complex is called faces or simplices, and maximal faces of a simplicial complex are called facets. So I will always say complex rather than saying simplicial complex all the time. So when you observe that you collect facets in a complex, then you have to take all possible subsets of a facet. So it's sort of makes sense to denote a simplicial complex using the facets available in the complex. So the dimension of a face is the cardinality of the set minus 1, and dimension of a complex is the maximum of the dimensions of all the faces available in the complex. And we say a simplicial complex or complex is pure if all the facets have the same dimension. For example, you take this complex where the maximal faces are 1, 2, 3, and 3, 4, 5. Since both have the same cardinality, this complex is called pure. On the other hand, you take 1, 2, 3, and 3, 4.
So, sorry,
Yeah.
facets are the maximal faces, is it?
Yes, correct. Maximal faces are called facets. So, for example,
It is supposed to be generated by the maximal faces rather than the vertices, I see. Aha.
yeah, so I said if you write the facets, you sort of know what a simplicial complex is because you take the facets and all possible subsets of the
All
facets
possible.
available.
Very good. Okay, thank you. Thank you.
So the complex where you have facets 1, 2, 3, and 3, 4 is not pure because both the cardinality of both the facets are different. So a complex is called pure if the cardinality of all the facets are same. Now let's just quickly let me tell you what the geometric realization of an abstract simplicial complex is, because the definition is just through the sets and the collections, right? So in algebraic topology first course, we just go through a geometric complex where we say a vertex is a 0 simplex, edge is 1 simplex, triangle is 2 simplex, and tetrahedron is 4 simplex, and so on. So these simplices are denoted as sets in abstract simple complex. A singleton set, maybe a power set of a singleton, is a vertex. Power set of a set of cardinality 2 is an edge. Power set of a set of cardinality 3 is a triangle, and so on and so forth. So there is a one-to-one correspondence between abstract simplicial complex and geometric simplicial complex that we have, where the geometric simplicial complex is collection of geometric simplices with the property that two simplices must intersect in a face. Yeah, so for this talk, I will not differentiate between abstract simplicial complex or geometric simplicial complex. Both the things will be same for me. Yeah, one more thing, I have written these notes by hand, so if you don't understand a word or something, just let me know. So now let me come to the main object of this talk, which is graph complex. A property of graphs is called hereditary if whenever a graph satisfies the property, then all the induced subgraph of this graph also satisfies the property P. So let me just say what the induced subgraph mean. So when suppose you have a graph G and you say H is an induced subgraph. When do you say that? Whenever you have two vertices in H and these two vertices are adjacent in graph G, then they must intersect. They must be adjacent in graph H. For example, you take the graph G here, 1, 2, 3, 4, 5. Then the graph 1, 2, 3 is the induced subgraph. On the other hand, this graph is not induced because this misses the edge 2, 3. So I hope this induced subgraph definition is clear here. So let's just see one property which is hereditary in graphs. So a property is the complete graph property. So you know that the complete graph is a graph in which any two different vertices are adjacent. So when your graph is complete, all the induced subgraphs are also complete. So this definitely is a hereditary property. So what a graph complex is, suppose you have a graph. Now you also have a graph property which is hereditary, say P. Then the P graph complex is collection of all the subsets of the vertex set of G with the property that GS, the induced subgraph on the vertices S, has the property P. Let's see this via an example. The example is again the clique complex where you have taken the property P being a clique. So if you have the graph G 1, 5, 6 and 2, 3, 4, now you have to collect all the subsets of vertices which form a complete graph in this graph G. So what are those subsets? 1, 5, 6 is a subset which is a complete. Again 1, 2 is a subset which is complete and 2, 3, 4 is a subset which is complete. So the facets of this complex are 2, 3, 4, 1, 5, 6 and 1, 2 geometrically, which is same as this simplifier complex that we have. The other very important complex that that has been associated with the graphs is neighborhood complex. Now, why this complex is important and why I'm putting this in this talk, I'll just tell you in a minute. But before, let's just see the definition of this complex. The complex is so the complex is collection of all the subsets of vertices of G with the property that this has a common neighbor. What do I mean by common neighbor? So you say sigma is a face of neighborhood complex if and only if there exists a vertex V such that sigma is subset of neighbors of V. So let's just see it by an example because maybe the definition is confusing. So let's just take the graph G. So what are the simplices you have? You collect 3, 4, 2 and you see that because this set has a common neighbor 1, you put it in the simplifier complex. Similarly, you take say 1, 2, 3. Now when you take the set 1, 2, 3, you see that in the graph set 1, 2, 3 does not have a common neighbor. So it is not a face in the simplifier complex. So these are the only facets that you get. Sorry, this should have been angle bracket. Yeah. So yeah, this neighborhood complex is collection of all the facets 2, 3, 4, 1, 2 and 1, 3. Geometrically, this is what you get. Now let's take another graph and try to see what the neighborhood complex of this graph is. So more or less, what do? You take a vertex, you collect all the neighbors of this vertex and make it a face in the graph, in the complex. So let's say I have taken 3. What are the neighbors? Neighbors are 1, 2 and 4. So 1, 2, 4 is a simplex in the complex. Similarly, you take 4, then neighbors are 3 and 5. 3 and 5. Oops. 3 and 5 is again a face in the complex. Similarly, you take 5 and collect all the neighbors. You take 8 and collect all the neighbors and so on. So this is how you get the neighborhood complex. Now, why this neighborhood complex is important is because this was the first complex which was associated with graph and which turned out to be the origin of now called the topological combinatorics. So this work was done by Louvaz in 1978 or so. So let me recall a definition of chromatic number of graphs. The chromatic number of graphs is the minimum number of colors required to properly color vertices of G. What do you mean by properly? Properly means if two vertices are adjacent in graph G, then they must receive different colors. So Kneser in 1955 conjectured that the chromatic number of the Kneser graph is k plus 2, where the Kneser graph is defined as follows. The vertices of Kneser graphs are all the subsets of 2n plus k with whose cardinality is n. And two vertices are adjacent in the graph if and only if they are distinct. For example, let's see what the KG21 is. KG21 is vertices are all the two subsets of 5. So these are all the two subsets of 5s and the adjacency depends on if they are disjoint. So 1, 4 is disjoint from 3, 5, you have an edge. And it's not difficult to see that the chromatic number of this graph is 3, exactly 3. And this is very famous Peterson graph. So yeah, so the conjecture of Kneser was the chromatic number of all the Kneser graphs are exactly 2k plus 2. Now, this conjecture was given in 1955 until 1977. There were many bounds available in graph theory and none were sort of goes to the...
Sorry, can you go down a bit?
Yeah, sure.
So what is G and K?
KG and K, yeah. So KG and K is called the Kneser graph.
Okay.
Oh, I sort of, yeah. So this is KG.
Ah,
KG and K is called the Kneser graph, where the vertices of the graphs are all the subsets of 2n plus k. 2n plus k, I just forgot this is set 1, 2 up to 2n plus k. So you collect all the subsets of set 1, 2 up to 2n plus k, whose cardinality is exactly n.
okay.
So yeah, for example, when I say what KG21 is, what do you do? The vertices are all the two subsets of the set 1, 2 up to 5.
Okay.
So these are all the two subsets of 1, 2 up to 5, and two vertices are adjacent if they are disjoint. So for example, 1, 4 is disjoint from 3, 5. 3, 5 is disjoint from 1, 2, and so they are adjacent. And 3, 5 is not disjoint from 4, 5, so there is no edge between them.
So, and the conjecture is that, so you've shown that this has chromatic number 3 and the Euler characteristic of this is 3, is it? Okay, okay, that is.
No, this is
Fine.
not Euler characteristic. This is chromatic number of graph.
No, but then what is the conjecture?
The conjecture is the chromatic number of these graphs are exactly k plus 2
K
for
plus 2.
any n and k.
Okay.
So this was conjectured in 1955. Until 1977, it was not proved, and since there were many bounds available in graph theory already, but none of them were closed. Then Loas came up with a very wonderful idea of proving this conjecture. What he did, he took a graph, he associated the neighborhood complex with this graph. He computed the connectivity of this graph, of this simplicial complex, and then gave a lower bound for the chromatic number of graph in terms of the connectivity of the neighborhood complex, where the connectivity of the complex is the maximum case such that all the homotopy groups up to k are trivial. So here sort of I'm abusing the language of pi 0 and pi 1 in the sense like they are not groups, but yeah, pi 0 is not a group, but still I'm just writing it. All the pi i's till k are trivial. So that's the connectivity of the complex is. So what Loas proved is you take a graph, you associate the neighborhood complex with this graph, then the chromatic number of graph is always bounded below by the connectivity of the neighborhood complex plus 3.
What
And
is X here?
is chromatic number
No,
is
this c- uh, this
oh
X
yeah,
this
so this is a should have been ng. Yeah, this is any complex that you talk about.
okay.
So connectivity of any space or any simplicial complex is sort of maximum of k such that the homotopy groups up to k of of this complex is 0.
Okay.
Yeah, so what Loas did is he found a low bound for the chromatic number of graphs in terms of the connectivity of the neighborhood complex. And it turned out that this bound, in case when you restrict your graph to be Kneser graph, this bound is tight. He showed that the chromatic number of kg and k is bounded below by k plus 2. And it's not very difficult to color this graph with k plus 2 vertices. So it turned out to be exactly same. So he proved this conjecture by assigning a simplicial complex to a graph G. And this was the origin like birth of the topological combinatorics area, which is now actually people are working in this. And after this, there were many simplicial complexes which were associated with graphs, and people have tried to sort of find the combinatorial properties of graphs with the associated simplicial complex. And there are many simplicial complexes which people have associated with the graphs. And one of them is the independence complex. And this is the main object of this talk. I'll just stick myself with the independence complex now. So, how this complex is defined? You take a graph G and you say a subset of vertices of G is independent if the induced subgraph does not have any edge. So the induced subgraph is just collection of isolated vertices. And you observe that the property of this property of being isolated vertices is hereditary. So what do I mean by that? If sigma satisfies this
Sorry,
property,
these are isolated from each other.
yes. So what do I mean by that? So let's just see this example. So you take 1, 2, and 3.
Yeah.
When you take the induced subgraph on 1, 2, 3, you get just isolated vertex 1, isolated vertex 2, and isolated vertex 3.
Okay.
So these are sort of isolated vertices as a graph. So G sigma does not have any edge. So this is K2 free, edge free graph. That's what you get. Then you call this sigma to be independent set of G. And independence complex is collection of all the independent subsets of vertex set of G. So let's just see why this is this by an example again. So what are the independent subsets of it? 1, 2, 3 is the maximal independent subset because when you put 4, this graph becomes connected. So 1, 2, 3 is 1 which is maximal and vertex 4 is 1 which is maximal. So this is what you get as
independent complex is actually a complex whose facets are the independent sets.
yes, whose faces are the independent sets. Yes. And this is sort of easy to see that if a collection is independent, all its subsets are again independent. So this makes it a simplifier complex. Because if you have G sigma does not have any edge, then G tau will not have any edge for any tau subset of sigma. Is that okay?
So, just
sorry.
one question. If you take a complete graph, then what will be the complex?
The complex will be just endpoints, end disjoint points.
Empty set,
Because,
huh?
because you take not empty set, there will be end disjoint point, just
Oh.
isolated vertices and end vertices.
Okay, you include singletons.
Because,
Okay.
yeah, because when you take any 2 points, they are connected.
Yes.
So they are not independent. So other example is when you take C6. Let's
Sorry.
just,
So
yes.
previous this thing.
Yeah, yeah.
So you see in the first 1 or 2 slides, this notation you had used. So within the brackets, that was the set of facets of a complex.
Yes, yes, yes.
Now
So
you are using that as a complex generated by a set, right?
no, these are the facets of this simplifier complex.
I
So
know,
1,
but
2, 3.
but you're saying this graph,
Oh,
right? You're taking the set and you're taking this the set of its subsets, and that's a complex that in G is, right?
yes. So
Otherwise,
this,
what does this mean?
this notation. That's what you're asking.
Yeah. So you have. I thought this notation meant these are the graph, and on the right you say these are the facets of the set.
Yes, yes. So independence complex is the complex whose facets are 1, 2, 3, and 4.
Right. And why should the facets determine the complex?
Yeah. So what is the simplifier complex when you have these facets? So what do? You take a facet, you put all the subsets of it in the complex. So this collection of facets uniquely determine the simplifier complex.
Always?
Yes.
Aha.
So when you have two simplifier complex which are different, then there must be one facet which is different. All the facets cannot be seen.
Okay. Okay. Fine. Okay. Thank you.
Yeah. So another example is when you take a cycle of length 6. So cycle is a graph. A cycle graph is a graph on n vertices, in which the edges are 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, and so on up to n minus 1 n, and then n is adjacent to 1. So here the C6 is cycle graph on 6 vertices. Now just let's see what the independence complex of this cycle graph is. So let's just see. You take a vertex V. Now you want to choose another vertex which is independent with 1. So the other choice is 3. You can take 1, 3 is independent. Now, can you put any other vertex which is independent with 1 and 3? That is obviously 5. So the set 1, 3, 5 is independent. So this becomes a facet here. Similarly, 2, 4, 6 is independent. This becomes a facet here. Now, you see 1, 4 is again independent. And if you take any other vertex with 1, 4, it won't be independent anymore. So 1, 4 is a facet. Similarly, 2, 5 is a facet and 3, 6 is a facet. So when you draw this complex geometrically, you get this topological space. That's what you get. Okay, so yeah, so the question is how general these independence complexes are. How general is it to find the independence complex? So this is not very difficult to see that you take any simplifier complex, then you can find a graph whose independence complex is homeomorphic to this simplicial complex. And the first result in this direction was due to Kozlow in 1999, where he found the homotopy type of independence complexes of cyclic graphs. He showed that the independence complex of cyclic graphs are homotopy equivalent to wedge of spheres. So this notation is wedge, where you take two complexes and join them with the point only. It's like this. Yeah, is it? Okay. So, yeah, so these are the independence complexes. Now, let me just talk about why these complexes are important in different areas of mathematics. The first one is definitely topological combinatorics, why it is important here. So here onwards, what I'll assume is all the complexes are pure. By that, all the facets are of the same dimension. Although whatever I'm going to discuss is
Yeah,
true
one
for
stupid question maybe. So when you say simplicial complex, that means it has only face, meaning two-dimensional.
no. It has there can be faces which are dimension more, but it's very difficult to draw. That's what I have not given. That's the reason I have
So
not
you are
given any
saying
examples.
any simplicial complex, there is a graph whose independent complex is.
Yes. So what I was trying to say is, you take any simplicial complex of any dimension. There is always a graph G whose independence complex is homeomorphic to the topological space K as a topological
Oh,
space.
I see. Thanks.
Yeah, so for me, like simplicial complex and the underlying topological space, they are sort of, I won't distinguish between them in this talk. So whenever I say complex space, and sometimes it means simplicial complex, as I said. Yeah, so in topological combinatorics, let me just define few things in which are sort of very important for this talk. So first is the link of a face in any simplicial complex. So suppose you have a complex K and there is a face sigma in K. So the link of sigma in K is collection of all the faces tau such that sigma intersection tau is empty and sigma union tau is in K. So let's see an example of it. Suppose this is your complex and you want to compute the link of the vertex 1. So what is the link of the vertex 1? You know that 2, 3, 1 is a simplex in this complex. So 2, 3 is the link. Again 3, 4, 1 is a simplex. So 3, 4 will be in the link. Similarly 5, 1 is a simplex. So 5 will be in the link. Okay. The link of 2 similarly is just complex 1, 3. And the deletion of a simplex in a simplex complex is all the faces whose intersection with sigma is empty. So you just remove everything which contains sigma and you are left with the deletion of sigma in K.
What
For
does
example,
sigma union tau mean?
I just said, so K is an abstract simplicial complex which is defined as a set collection.
Okay.
So as a set, you take the unions.
Okay, thank you.
Yeah, so for example, 2, 3, 1. 1 union 2 union 3 is a simplex in our complex. So the length of 1 is 2, 3, and so on and so forth. And the deletion of 2 is you remove all the faces which contain 2. So when you remove everything which contains 2, you are left with just 1, 3, 4 and 1, 5, which is this complex. Okay, so yeah, so I think this is clear because this is sort of very important for this talk, this link and deletions. Yeah, so let me define what vertex decomposability is. A complex K is called vertex decomposable if E is a simplex. By simplex, I mean either K has just one facet or there exists a vertex V such that both link and deletion are vertex decomposable and every facet of deletion is a facet of K. So this is sort of inductive definition that we have, but the applications of vertex decomposability are huge. So let me give an example here. Focus on this complex 1, 2, 3, 4. And why this complex is vertex decomposable? Because I can choose the vertex 1 and look at the link of 1. Link of 1 is the simplex 2, 4 and deletion of 1 is the simplex 2, 3, 4. So it satisfies this property because there exists a vertex such that both link and deletions are vertex decomposable as well as any facet of deletion is a facet of K. So this complex is vertex decomposable. Another object in this sequence is shalability. A complex is called shalable if you can order the facets in a way that whenever you take ith facet and intersect it with the union of previous ones which are occurring in the sequence, you get a pure simplicial complex whose dimension is same as the dimension of fi minus 1. So what do I mean by that is, like, suppose you have this simplicial complex. So there are 5 facets, right? You have a facet A, you have facet B, C, and D, and E. Now, what this definition says is that you can arrange these facets in such a way that whenever you take Fi and intersect it with the union of previous ones, you get a pure, and the dimension of this pure complex is exactly equal to dimension of Fi minus 1. And this is what the ordering of these facets here is. On the other hand, when you focus on this simplicial complex, this is not shellable. You can try any ordering of the facets of this complex, you won't get this property. So being a shellable complex is sort of very well studied notion, and it has many applications in topological combinatorics. One of the main is the following: that when you have a simplicial complex which is shellable, then the homotopy type of the simplicial complex is always wedge of a space. So a complex is called homotopic Cohen-Macaulay when for any phase sigma, the homotopy groups up to the dimension of link are always trivial. On the other hand, if you don't want to consider the homotopy groups, just focus on the homology groups, these complexes are called Cohen-Macaulay over the field F, where the field contributes in the computing the homology of these links. So this is sort of not very easy to give examples here, but these Cohen-Macaulay spaces are very well studied now, and statement of Stanley which says it would be nice if you can start a lecture by just saying that a simplicial complex is Cohen-Macaulay. And indeed nowadays it's like Cohen-Macaulay spaces are almost everywhere.
So homotopy Cohen-Macaulay is stronger than Cohen-Macaulay.
Yes, homotopy Cohen-Macaulay is very strong. So that's what we have in the next slide. People have proved that the vertex decomposability is the strongest in all the notions that we've defined recently. So vertex decomposability implies shellability, and shellability implies homotopy Cohen-Macaulay, which implies the Cohen-Macaulayness. The homotopy Cohen-Macaulay also implies that the complex is homotopy equivalent to wedge of spheres. And these inequalities are strict. That there are many counterexamples to this, and that is sort of, we'll take one lecture to talk about if you go in the counterexamples. So maybe I'll just skip the counterexamples here and go ahead with this. So in topological combinatorics, sort of very active area of research is the following: that you find simplicial complexes which belong to some class but not the previous ones. Okay. So independence complex have contributed in this direction as follows: that Woodruff in 2009 proved that if you take a caudal graph, the independence complex of any caudal graph is vertex decomposable. So it sort of satisfies the strongest property. And Francisco and Ventul in 2007 proved that when you restrict yourself to cycle graphs, these complexes are Cohen-Macaulay if and only if the length of the cycle is 3 or 5. So independence complex of C6 is not even Cohen-Macaulay. But we know that the independence complex of cycle graphs are wedge of spheres. So it sort of gives us a example which is wedge of spheres but not Cohen-Macaulay. And thereafter there have been many classes of graphs whose independence complex have been computed, and people have like sort of done a lot of work in this direction. This includes the Claw-free graphs, triangle-free graphs, stable and Kensler graph, and so on and so forth. There are many other classes whose homotopy type of independence complexes have been studied. The other direction that independence complex have connection with is combinatorial algebra. So what I'm going to do, I'll just talk about the edge ideal rather than taking any arbitrary square free monomial ideal. So suppose you have a vertex of the graph is 1 to up to n. Now you define the ring, which is a polynomial ring with the field f and whose variables are x1 up to xn. And the edge ideal of this ring is defined as the ideal generated by xi xj such that I comma j is an edge in the graph. So given a graph, you always have an edge ideal. And a very important problem and very active problem in the combinatorial algebra is the following. Can you obtain algebraic information of this quotient ring in terms of the combinatorial data of the graph? So to answer these questions, there are some methods that people do in algebra, and they are as follows. So given this quotient ring, you have a minimal free resolution, and in this minimal free resolution, the Hilbert-Sisky theorem and Ostrander-Bushbaum theorem implies that the length of this resolution is bounded below and above by these numbers. So this number I have denoted by D. So I'll be using this D in the next slide. So this length of this minimal resolution is always below and above these two numbers, and is sort of, I don't remember who proved it, but these minimal free resolution are unique up to the length of that is. Yeah. So this length, the integer n minus L is called the depth of this quotient ring that you have, and this inequality tells you that the depth is always bounded above by D. And when depth is equal to D, the ring AG is called Cohen-Macaulay. So there is a notion of Cohen-Macaulay in algebra as well. And we have seen that there is a notion of Cohen-Macaulay in topological combinatorics. So how these two notions are related. And in fact, they are same in both the notions. What do I mean by that? I'll just explain it here. So you have a monomial square free ideal, and you have on the other hand a simplicial complex. So these two are in one-to-one correspondence. The correspondence is as follows. Suppose you have a complex K. So how do you define a monomial ideal? Monomial ideal is generated by all the monomials I1 up to Xij such that I1 up to Ij is not a face of K. You take all these monomials as generated of the ideal. And this ideal that you get is called Stanley-Reisner ideal associated with the complex K. Now when you take the quotient of this ideal, you get f of x1 up to xn, where n is the number of vertices quotiented ik. On the other hand, you have the complex k. So the Cohen-Macaulayness of this complex is same as saying the Cohen-Macaulayness of the ring that you get as a quotient. When you restrict yourself to the independence complex, the ideal that you get is the edge ideal. And the commutative properties or the algebraic properties of edge ideal have been recently studied a lot by the people, by the researchers in commutative algebra. And one of the main object that they study in this direction is the following. So you know that there is a free resolution of a quotient Ig, where all the modules that are occurring in this resolution are of the following type, where A minus J is shifted module of A, and beta Ij denotes the number of times how many times this A minus J occurs in Fi, where Fi is this, like this is F1, this is F2, and so on, this is Fl. And beta Ij are called Betti numbers of the quotient ring. Now, Hoxton in 1977 proved that these Betti numbers of the quotient ring can be computed by the dimension of the homology or the reduced homology of some induced subcomplexes of the complex G. So it's sort of, you can compute the this Betti table using algebraic methods, as well as you can compute the independence complex and the induced subcomplexes of it and compute the homology. This will also give you the beta table of the quotient ring. So this sort of, you can study these complexes and compute the beta table for the quotient ring. And the other notion which is very well studied for the ideals is the regularity of the quotient ring that you have. So regularity is defined as the maximum j minus I, where the beta ij is non-zero. Now, how this regularity is related to the independence complex? Now, the regularity of the quotient of this quotient ring, how this regularity of quotient ring is related to the combinatorial information of independence complex, and this is how it is. So the regularity of the quotient ring is the regularity of the independence complex that you have with respect to this field f, where this number is called the Leray number of the complex independence complex, where the Leray number is maximum over all I such that homology or the reduced homology is non-trivial for some induced subcomplex L. So this is sort of the motivation behind doing these independence complexes, which can help computing the regularity of the ideals as well as the beta table of the quotient ring that one has in the commutative algebra. Yeah, so the other direction which is important is the same with the motivation of which every this simplest complex thing were started. So let's come back to the graph theory, which was the original motivation for studying these simplest complexes. How these independence complexes help us get the combinatorial information of graphs. And in Burmark in 2010 proved that the chromatic number of the graph is bounded below by the strong LS category of the independence complex G plus 1, where the strong LS category of a complex is the minimum n such that you can cover K with n plus 1 contractible. Is this clear so far? So this is what the relation one has with the chromatic number and the independence complex. And there is one more notion of graphs which is related to the independence complex, and that is called the domination number. So at set S of the vertex set is called dominating set if for each vertex in Vg minus S there exists a vertex in S such that V comma U is an edge in G. So what it tells us that a set completely dominates the vertex set of G, vertex set of G minus S. On the other hand, the strong dominating set is the set which dominates the whole vertex set of G. So mathematically what it tells us that a set S is called a strong dominating set if for each vertex in Vg you have a vertex in set S such that V is adjacent to vertex W in the graph. And the domination number as well as the strong domination number is the cardinality of the minimum dominating set. So for example, if you have this graph in the left, the domination number of this graph is 3 because you can take 2, 3 and 4. It will dominate the whole graph. And the strong domination number of this graph is 4. So this is, you can check that if you take 2, 3, 4 and 1, this is strong dominating. But anything smaller than 4 will not strongly dominate this graph. So Meishigam in 2003 proved that if the strong domination number of graph is bigger than 2k, then the reduced homology of the independence complex are 0 up to certain stage. Similarly, if you have a caudal graph, then this bound can be improved in the sense that if you have a caudal graph and the domination number of G is bigger than k, then all the homologies up to level k minus 1 vanish. So this is sort of this relation between chromatic number and domination number was sort of motivation for us to see to define whatever we did in our project. And there is a generalization of these two notions in the graph theory. So let me just define what those generalizations are. The generalization for the domination number is distance R domination number. So distance R domination number is defined as follows. You take a set, you say the set is distance R dominating. If for all vertices in G, you can get a vertex in W whose distance from V is at most R. So this is same as saying V and W are connected by a path of length R. Okay. And the strong distance R domination number of a graph G is the minimum of cardinality of all the distance R dominating sets of G. So for example, if you take this graph and you try to find out what is the strong one domination number of this graph, this is same as the domination number. It comes out to be 4. And the strong and the distance to domination number of this graph is 2 because you can just take vertex 1. It is adjacent to any other vertex with at most distance 2. So it is sort of the length between this vertex and any other vertex is at most 2. So this dominates this whole graph up to length 2. And the generalization of the chromatic number that we have taken into account is the following, which is called clustered R chromatic number of a graph, where cluster or chromatic number is defined as follows: the minimum of n such that there exists the coloring of graph G with n colors with the property that any induced subgraph on any color class does not contain a connected graph on R plus 1 vertices. So it's sort of, when you restrict to a particular color class, all the connected components have cardinality at most R. When you see this example, the one clustered chromatic number is same as the chromatic number, which is 3, and two clustered chromatic number of this graph is again 3, because let's try to color this vertex with, say, color blue. So when you color this vertex with color blue, you can again color this vertex with color blue, because you'll have at most two, the same color will sort of induce a subgraph of cardinality at most 2. But when you have these two, you cannot color any other vertex with color 2. So you have to color 3, 4, 5 with few different colors. So how many colors you need to color 3, 4, 5 with the property that any color class should not induce a connected component of cardinality at most connected component of cardinality 3. So you can color 3 with red, 4 with red. You have to color 5 with a different color. So the distance to chromatic number, clustered chromatic number of this graph is 3. So these two were the motivations behind the complex that we have defined. What we thought is, can we get a simplified complex which will give us a topological bound for these two numbers that we have. So this is called higher independence complexes, and the higher independence complexes are defined as follows. For r greater than or equal to 1, a set S is called R independent if every connected component of induced subgraph GS has at most R vertices. So it's sort of generalization of the independence complex, because when you take R equal to 1, it just tells you that all collection of independent sets. A set is independent if there is no edge in the induced subgraph. So we're relaxing this condition and we are allowing all the connected components of cardinality up to R. So R independence complex of graph G, denoted in RG, is a collection of R independent subsets of G. Let's see this by an example, because this is not straightforward to see it as it is. So let's just see what this graph is. Let's take this graph 1, 2, 3, 4. We have seen that the independence complex of this graph is this triangle 2, 3, 4 and isolated vertex 1. Now what is int 2 of this graph? So we are allowing all connected components of cardinality up to 2. So 2, 3, 4 is there because 2, 3, 4 is one independent. And other than that, 1, 2, 1, 3 and 1, 4 you will allow because they are two independent, and that's it. You cannot have 1, 2, 4, 1, 2, 3, 1, 3, 4, 1 and so on. The other example is C5. The C5 into 1, we have seen that this is again, you get C5, not C5, but this is simply a complex 1, 4, 2, 5, 3, 5 and 1, 5. And the int 2 of this graph is this simplest complex that you get. I have drawn these curved lines, but these are not curved actually. I cannot embed it in R2, so I had to sort of draw it curved. So is the definition clear so far, sir? Actually, yeah, so I'll go ahead with this. Yeah, so let's just see some simple observations. Now, when you have two disjoint graphs, you take the disjoint union of two graphs, the R independence complex of these two disjoint unions comes out to be int R of G1 joined int R of G2. The join is a join operation defined in topological spaces. And the other observation is the int R minus 1 is always a subcomplex of int R G. So you get this filtration sequence for int R, where when you go on the top, you get a simplex. Okay. Also, you can take all the subsets whose cardinality is R. In the graph, you can take all the subsets whose cardinality is at most R. So what it tells you that the R minus 1th skeleton of this simplest complex is full. In particular, all the homotopy groups up to r minus 2 vanish. And as Professor Bigura asked, what is the int 1 of Kn? There were some sort of isolated vertices. What is int r of Kn now? Int r of Kn comes out to be r minus 1th skeleton of the simplex delta n minus 1. So this simplex is a simplex complex which has only one facet, and the cardinality of the facet is n. So this is the r minus 1th skeleton of delta n minus 1. And we have shown that the R independence complex of complete multipartite graphs are also homotopy equivalent to wedge of spheres, where the number is exactly this. Moreover, the independence complex of path graphs and cycle graphs also comes out to be homotopy equivalent to spheres or wedge of spheres. Yeah. So this is the main result that we have is when you restrict yourself with the caudal graphs, then the R independence complex is always homotopy equivalent to wedge of spheres. And we have also given the kind of spheres that will occur in the homotopy type. We have shown that if in the RG is homotopy, this should be homotopy equivalent to wedge of SITs, then IT should be of this form. This should be of form RK minus 1 for some K. Also, if you have any two sequences D1, D2 up to Dn and K1, K2 up to Kn, this is sort of a reverse of the part 2, where we have that if you have these two numbers, then you can construct this topological space, and then you can find out a caudal graph G with the property that int R of G is homotopy equivalent to this given space. Yeah. Now let me get back to the motivation that we started. Our motivation was to find out a topological bound for distance R domination number and cluster R coloring of graph G, of any graph G. So in this direction, we have the following result. Say homological connectivity of a complex is maximum n such that the integer homology up to level n vanish. So that's what a homological connectivity of a complex is. We have shown that this is sort of, this should not be here, maybe this is typo, maybe this line should not be here. So the first thing in this direction is the following: the distance R domination number of any graph is bounded above by this quantity. This quantity is homotopic connectivity of R independence complex minus R plus 2. And when you restrict yourself to caudal graphs, there is an improved bound, and the bound is the following. Also, there are examples when these bounds are tight. What do I mean by that? These bounds cannot be improved, so these bounds are best possible. For example, if you take R equal to 2 and G equal to C6, then the distance to domination number of C6 is 2, and the quantity on the right hand side that we have is again 2. Also, when G is caudal, this bound is also tight. Here is the example for that. When you take R equal to 2, G equal to path of length 7, then the two distance to domination number of P7 is 2, and the quantity on the right hand side is again exactly 2. So these bounds are very tight in terms of distance R domination number. And the relation of these complexes with clustered R coloring is still under progress. We have not got any sort of concrete result in this direction, but we hope to get some relation between the chromatic clustered R chromatic number of graph G and the R impedance complexes of graphs. Yeah, so let me just give some problems in this direction that we have. So we know that there is a strict sequence of this kind that we have. So the question in this direction would be, what is the R independence complex of Pn and Cn? We know they are homotopy equivalent to wedge of spheres. So where do they belong in this sequence? Are they Cohen-Macaulay, or are they homotopy Cohen-Macaulay, and so on? Similarly, for caudal graphs, where do they belong? Because we know that int 1 of G is vertex decomposable. So do int R of G always vertex decomposable whenever you restrict yourself to caudal graphs? And can we compute the Leray number of R independence complexes of graphs? Because this will help us find out the regularity of R edge ideal, which is defined similarly as the edge ideal. And one more general question is how general these complexes are. In fact, can you, for given any simplified complex which satisfies certain properties, can you get a graph whose R independence complex is homotopy equivalent to this simplified complex? Yeah, and the fifth question is, I told you that sort of we are working on it, and we are hoping to get some relation between clustered R combinatoric number and R independence complex of graphs. Yeah, that's it.
Thank you, Anurag. Are there any questions? Okay, so if there are no questions, let's thank Anurag for a very nice talk.
Thank you.
Thank you.
Yeah, thank you, sir.